Hi dear student friends, so myself Manjunatha PC, so working as a senior assistant professor in the Department of Computer Science and Engineering, Reva Institute of Technology and Management, Yelahanka, Bangalore. So in continuation to with my previous sessions, I would like to continue this session on the same topic, functions, arrays and strings. So before we proceed to this session, so let us see what we have learned in the previous session. So in the last session we have seen like what exactly the searching problems are, and so the two different methods what are there under searching problems, that is linear search and binary search. We have seen initially the linear search with an example, and then we have seen the algorithm of linear search, and also we have seen how to transform an algorithm of linear search into a C program. And later we have seen the concept of binary search, and we have studied even the example of binary search, and we have seen even an algorithm of the binary search. So in this session, so we will be studying at the end of this particular session, we will be knowing like what exactly the binary search algorithm and how to transform that into a C program. So here we revisit the binary search algorithm again, and we try to transform that into a C program. And then we will see the comparison between a linear search and the binary search algorithms and the programs, and then we will see the concept of sorting problems. Under the sorting problems we will see here one particular method called a binary bubble sort method. So here we see the examples of bubble sort, the algorithm of the bubble sort, and then the associated C program. After transforming the algorithm into C program, what we get there. And also we will see the modification that can be possible in the bubble sort, so that it can improve the performance of the bubble sort. And finally we look into the concepts of the two-dimensional arrays. So if you look into the binary search algorithm, so in the last class we have seen like, so the algorithm statements goes like, the first we read the number of elements, the n, and then we read the n elements of an array, and then we read the key element that is to be searched in the list of a sorted list of elements. Here we have to make sure that the number of elements what we read here, it must be a sorted list, because binary search works only on the sorted list of elements, whereas linear search works both on a sorted list as well as a unsorted list, whereas binary search will works only on the sorted list. So here read n elements of an array A, it has to be mentioned like it has to be in the sorted order only. So then we initialize here the two variables low and high as 0 and n minus 1 respectively. Fine. So initially we set like flag is equal to if false. We assume that the key element is not present in the list. So after that, so when you go into the loop, we will initially calculate the middle element here. So mid is equal to low plus high by 2, and then we compare key is equal to a of mid or not. If the key element is present at the middle of the element, so a of mid, so here most of the students will write here just key is equal to mid. It's basically not key equal to mid, rather it is the element at the middle position. So it has to be taken as key is equal to a of mid. Then so I declare like flag is equal to true and I break. So I stop my execution of this binary search algorithm, and here I declare that the element is present. So here when I break here, I will be coming out of the loop. Once I comes out of the loop here, once again I will check here flag is equal to true means I will print the successful search, and then I terminate the execution of this searching algorithm. And in case if the key is greater than the middle element, then possibly the key, in case if it is present, it has to be present in the right half of the array or the higher half. So since when you are going to the higher half, the higher pointer, the high value remains constant, and we have to alter the lower value, and low value is taken as here mid plus 1. So this you should keep in mind when you are programming it. And then else, if key is not equal to a of mid, and if key is not greater than a of mid, so then obviously the key has to be lesser than the a of mid. So in case if the key is lesser than the a of mid, so we have to go for the lower half of the sorted list of elements. So when you are going for the lower half, the low will be kept constant, whereas high has to be taken as the position mid value minus 1. So that is high is equal to mid minus 1. So this process we continue until low less than or equal to high. So in case if the key is found here, so then flag is equal to true, break, I will be coming out of the loop. In case the key element is not present in the list, that is if it is unsuccessful search, then the condition low less than or equal to high will fail. So the low will exceed the high value, and I will be coming out of the loop. When I am coming out of the loop in this situation, the flag remains as the false. We have not set the flag as true, and hence if flag is equal to true, I print successful. If it is set as false, then we say like unsuccessful search. So let's write the C language code corresponding to this particular algorithm. So here the first basic the inputs of this algorithm is reading the number of elements n, then reading the n array elements, and then the reading of the key element. So here the statements of the function will be like first we have to declare n, the number of elements, and then a of n, the array of n. So instead of n here, we specify here 50. So a of n is not possible, we say here a of 50. That the subscript what mentioned here, the size of the array, it must be a constant. We specify there a of 50, and we require one more variable called flag. And then, so initially the flag is set as false. We can set here itself. So false means it is the value 0, and we require two more variables, that is low and high. And to read the elements of an array, we require one more variable called I. So these are the variables which are essential for programming this particular binary search. Then we have to write the printf statement to read the number of elements. Printf. So here I just mentioned the dash. I assume the students are aware of what statement has to be framed over there. So then the scanf. So I will be reading the number of elements as scanf %d ampersand n. So after reading the number of elements, so we print here. Again we go for the printf statement for seeking all the n elements of an array. So here we must mention like, so enter n elements, or we can say like %d elements in sorted order, because we are working on the binary search here. So we must take the input as the sorted list of elements. So for reading the elements, you know that we have to make use of the loop for I is equal to 0, I less than the number of elements. So then I plus plus. So here I write the scanf here itself, since I have only one statement, scanf %d ampersand a of I. I will be reading all the n elements of an array. Even if I write here, it is the same effect what I get. Even if I write here, I have only one statement within the body of this particular loop. I have only the scanf statement. With this, I will be reading all the n elements of an array in the sorted order. So here the input should be in the sorted order. If it is not in the sorted order, then the binary search will not work in the expected way. So then after this, we are supposed to read the key element. We have to note that the key element we have not declared here. So we must mention that the key also should be declared over there. So let us declare the key also, and then so we read for the key element. So I make the statement to be written by the student, and then I read the key element scanf %d ampersand of key. Now, so after reading the key element, now I have to transform the algorithmic statement of binary search algorithm into the programming statement. So here I will take the loop as. So initially we have to set the low value and the high value before we enter the loop. So here low must be set as 0 and high must be set as n minus 1, where n is the number of elements of the array, and flag also should be set as 0, but initially I have already set here flag is equal to 0 over there. So here, so all the required initialization of the variables we have done here. Now we can move to the looping construct. When you go for the loop here, so we have to be in the loop until certain condition low is less than or equal to high. Until this condition is true, we have to be in the loop only. So once we enter the loop, the first step here is we have to calculate the mid value. So note that we have not declared the mid value. Whenever the variables are necessary in my program, so that variables must be declared. Otherwise, so we get an error as undefined symbol. So here the mid has to be declared. So here we compute the mid value initially as mid is equal to the lower index value plus the higher index value, this complete thing divided by 2. Fine. So this will give you the mid value. First we have to compare now whether this mid value is equal to the key or not. So that is if key equal to a of mid. So note that here key equal to mid will be wrong. So here it has to be like key equal to a of mid. If key is equal to a of mid, we have to say like, so key element is present in the list and we have to exit from the loop. So here we write like printf successful search and we have to set So, instead of this, since we have taken the flag variable, finally we can write this successful search. So, we just set here flag is equal to 1 and we write the break statement. So, this break will take us outside the loop, it will take us out of the loop there. So, now we have to take another condition here, else if key is greater than a of mid. You can note that all these are statement, it is similar to the algorithmic statement. We are just converting that into a programming statement. If key is greater than a of mid, we have to go to the right half. When you are going to the right half, the lower index has to be moved, the higher index will be kept as it is. Else if key is greater than a of mid, then we set as lower index equal to the mid plus 1. So, else means obviously the key has to be like less than a of mid value. When it is lesser than the a of mid value, we write like high is equal to mid minus 1. So, then this we should keep doing within the loop. So, once we come out of the loop, either we have come out of the loop with this break statement or by the fail of this particular low less than or equal to high. So, after coming out of the while loop, if flag is 1, you have to print that the element is present in the search in the list and the search is successful, and in case the flag is still it is 0, then you have to conclude that the element is not found in the list, so that is unsuccessful search. So, I just continue this is so I just stop here, so that you can continue the remaining statements based on the condition of the y. So, flag status, we can compute whether the key element is present in the list or it does not present in the list. Now, if you look at the same code here, so here we see the same statements here. So, we have declared all possible elements that were required here, high, mid, low, I, and the number of elements, key, and all the elements over there. We read the number of elements, and this must be read in the sorted order only. Then after that, so here we read the number of elements, and all the number of elements must be read in the sorted order. So, after that, so we read the key element, and then we initialize the low value as 0, high value as n minus 1. So, the condition has to be like, while low is less than or equal to high, we compute the mid value as low plus high by 2, and if key value is equal to a of mid, we set flag is equal to 1 and break. So, we will be coming out of the loop if we found the key element in the list. So, else if key is greater than a of mid, we are going to the right half, and when you are going to the right half, you are setting low is equal to mid plus 1. Else means, so the key is less than the a of mid, so we set high is equal to mid minus 1. So, here we will be in the loop until either we come out of the loop by means of break statement or by means of failing of the low less than or equal to high condition. So, once we comes out of the loop, we check the condition if flag is equal to 1. So, then we print like successful search key found. So, else means we will print like unsuccessful search key is not found. So, here we have to mention those two statements in the board. So, here we can see that in the program what I have written on the board here. So, here after coming out of the loop, I should check the condition here if key is if flag is equal to 1. So, means the successful search. So, else means it is an unsuccessful search. And you can note a bit modification which you can do here in this particular program is we are just telling here like successful search. We are not particularly telling the position of the key element in the list, and we have seen in the previous example in the session. So, always whenever the key element is found in the binary search, so the position of the mid value whatever it will be there, so that will be the exact position where exactly the key element will be present in the list. So, is the reason key is equal to a of mid. If this condition is true, means what? The mid is pointing to the position of the element, so which is under search, right. So, here we can print like successful search key found at position percentage d. So, my statement could be like, so here I just write only that particular statement. A bit modification just to print the position of the elements. So, here I can print like printf element found at position percentage d comma mid. So, else means it is an unsuccessful search. Here no need of having any the printing of the positions, because it is unsuccessful search, we no need to write anything over there. Only in case of successful search we have to print even the position also if required. So, this is how we can transform the algorithm of binary search into a program. So, now let us see now the comparison of linear search and the binary search. And so, we see here linear search can be used over an ordered and unordered list of elements. So, linear search, there is no constraint that I must work only on the ordered list of elements, I mean the sorted list of elements. I can perform even on unsorted list also. That is what. So, I have stated an example in the previous session. So, if you want to search for your blue book in a bunch of blue books, whether the blue books are sorted or unsorted, you can easily search for your blue book. Fine. So, then the only problem with the linear search is it will take more amount of time for its computation. To confirm whether the key element is present in the list or not, the linear search will take a more amount of time. So, for example, in the bunch of blue books, if you want to look for your own blue book, then obviously if the blue books are sorted, you can easily get your blue book, and if the blue books are not sorted, then you have to compare. So, each and every blue book with your USN, and until you find your blue book, you have to go on searching, taking the blue books one by one. And if you look into the binary search, the binary search can be used only on the ordered list of elements. So, binary search is applied only on the ordered list, means if the lists are sorted, only then we can perform the binary search, and it is not mandated that elements has to be in increasing order or in the decreasing order. Fine. So, it can be in any order, but the thing is, if the elements are in the decreasing order, so instead of going to the right of in the previous examples what you have taken, we have to go to the left of. So, and vice versa. So, when the midways, so normally if the elements are in increasing order, if the key value is greater than the mid value, then we go to the right of, and if the key value is lesser than the mid value, so then we go for the left of. That has to be vice versa. So, in case of the elements are in a decreasing order. So, that is the only modification, but binary search expect that the elements of the array should be in the sorted order, and the binary search takes less amount of time. So, compared to the linear search here, the binary search will take the less amount of time. So, this is the advantage of binary search, that so it takes a less amount of time compared to the linear search. But the advantage of linear search over the binary search is like, so linear search can be so applied over even the ordered list also, and even in a unordered list also. Fine. So, that is the advantage of linear search over the binary search. So, next we will see the another problem, so called the sorting problem. Basically the searching and sorting are the major problems which we apply on the arrays, or I mean the list of elements, right. So, in case of sorting problem, here the problem is to converting an unordered list of elements into an ordered list. So, I mean if it is unsorted, we may need to sort the elements in the list, and when I say the term here, the ordered, it can be in any fashion. It can be like an increasing order of the elements, or it can be like decreasing order of the elements if I am considering some integer values, and if I am considering a character, then I may need to arrange the characters in the alphabetical ordering, and if I am taking certain dates, certain events have occurred in so and so dates, and if I have the list of date and times, I may need to arrange the dates and times in the chronological ordering. So, even that is also the one way of ordering. So, here the problem of sorting is like we take the unordered list of elements and we arrange them in a ordered fashion. Say for example here, so if I have the list of integer elements 21, 15, 43, 67 and 17, you can note that these particular 5 elements what I have here, so all these are unsorted, and here I have the same elements in the sorted order 15, 17, 21, 43 and 67. So, here it is in the increasing order. Similarly, if I want, I can program to get the elements in the decreasing order, right. So, this is a way of sorting, and if I have say for example the characters in the array, so then here we can say E, L, A, G, U, we have certain characters here, and we need to arrange the characters in the alphabetical ordering, then I can have like A, E, G, L, U is the sorted order or the ordered list what I can get here. So, basically we do not in special cases we go for a sorting of the characters, but in most of the cases what we do is we go for sorting of the names. So, when you are going for sorting of the names, you have to go with the alphabetical ordering only. It is like even in the dictionary also we find the words in alphabetical orders only. So, now this is one application, dictionary is one application where we find the name, so particular the words arranged in the alphabetical ordering. So, now so we will see the one particular the very interesting algorithm. So, that is bubble sort is the one which is used for performing the sorting of the integer elements, or it could be even names also, right. So, what exactly we use we do in case of a bubble sort. So, here we have to look at the term bubble. Say for example, the term why we are using here the bubble is, so in a water if you place any an object which is not floatable, so then obviously the bubbles comes up. So, the bubble which which is having the more volume of air, that will comes out first. So, here also with the same strategy we call this particular method as a bubble sort. We will see here how exactly the bubble sort will perform the sorting of the elements here. So, in case of bubble sort, we have to bubble up the largest element. Bubbling up the largest element is the major operation which we will be performing in the bubble sort. So, here we scan the elements of the array from left to right, and we bubble the largest value to the end using the pairwise comparisons followed by swapping if necessary. You will get to know once we are performing the bubbling up procedure over this particular list of elements. Now, if you look at this particular array of elements here, so here this is an array of 8 integer elements. The index will run from 0 to 7 here, and I have different 8 unique elements here, and if I want to arrange the elements in increasing order, then you just note that the 84 what is there, that is the highest element in this list, and this must guess the last position. So, we will see how exactly the bubble sort will work. So, as per the bubble sort, we have to move the in the array we have to move from left to right in the list. So, that is, this is the list of elements from the first 0th element to till the last element. We traverse across the list of elements, and then we have to compare each and every element, so followed by swapping if necessary. Now, so look at this. First we have to compare the 22 with that of its next element. So, here, so 22 and 15 is being compared. Look at the second step that is to be followed here. The bubble the largest value to the end using the pairwise comparison. Pairwise means always the adjacent element must be get compared, and in case the first element is greater than the next element, I should go for the bubbling up. That is, so I should go for the next position, means I need to exchange there. Now, I will compare here 22 and 15 here. When I compare 22 and 15, so I confirm that the swapping has to be done there. Swapping means interchanging of the values there. The A of 0 value is 22 and A of 1 value is 15. If I am calling this array name as A, then A of 0 is 22 here, A of 1 is 15. 22 is greater than 15, I supposed to swap it. I need to exchange it because the 22 is greater than the 15. As a consequence of swapping, so I will get the elements as 15 followed by 22 there. So, now, so we have to compare the second pair, that is now 22 with the 43. So, when I compare 22 with the 43, I should see whether the first value is greater than the second value or not. So, in this situation, since 22 is not greater than the 43, I no need to do the swapping there, because already the 43 is a greater value. So, that has to be in its position only. So, next I should go for the next pair of elements to the comparison. So, here 43 and 17 I compare. So, now we see the 43 is a greater value compared to 17. So, I need to perform the swapping there. So, 43 is exchanged with the 17. The 17 comes back to its 43 element position, and 43 will go to the 17 element position. So, that is, so here the 43 will bubble up because it is the highest value. So, next I supposed to compare 43 with the 67. Now, 43 is again lesser than the 67, no need of swapping. So, next we proceed. 67 we compare with 84. So, 67 is also lesser than 84, no need of swapping there. Next we will see, so 84 and the 25. 84 is higher value than that of the 25. So, I need to bubble up this particular largest value. So, here also, so 15 and 22 we have exchanged, 17 and 43 we have exchanged, but these are also the bubbles. But the thing is, the highest value what is there, that is of more interest, because that has to be taken to its proper position. So, that is what we are trying to do here. So, 84 is greater than the 25, our decision is to swap. So, when I swap here, the 25 will come to 84 element position, and 84 will go to the element 25 position there. So, now again I have to do the comparison of 84 with the 14. 84 is greater than the 14, I must do the swapping there. So, now after exchanging, so I get 84 in the last position. Now, 84 has to be compared with the next pair of the elements, but here you can note that, so the number of elements have got exhausted here. Since no more elements exist, I can conclude that, so 84 has taken its proper position in the list. So, thus largest element bubble up to the last position. This is how the bubble sort works. We start comparing every pair of elements, and wherever, so the first element is greater than the second element, I go for exchanging it. So, this is, I am arranging the elements in the increasing order. So, is the reason I have taken the decision as, if the first element is greater than the second element, then I exchange. If I take the decision as, if the first element is so lesser than the second element and then I exchange, then I can do like, so I have to go for the arranging the elements in a decreasing order. So, that's based on, so the requirement, you can do that particular operation. But the bubble sort here, what I have taken an example is like, I am arranging the elements in the increasing order. So, after performing so many bubbling ups here, or so many swappings here, you can conclude that 84 has taken its proper position, which it's supposed to get in the sorted order. If I sort this in any method, obviously the 84 should get into this particular position only. So, here so we did so many bubbling up there, comparison with each of the elements pair, and finally the 84 has taken its proper position there. So, now but here certain things we need to note here, like so only the 84 has taken its proper position, but still the remaining elements are in the unsorted order, that is in an unordered way. So, only the 84 has taken its proper position here, because this was the original list there, and after performing the first bubbling up procedure or the bubbling up method, so only the largest element, which was 84 present in the 5th position, was moved to the 7th position. Fine. So, meanwhile, so it has done so many modifications in the process of bubbling up. So, 22 and 15 it got exchanged, you can notice here, and even 43 and 17 also got exchanged, notice here, and further. So, finally 84 has exchanged with 25, and finally 84 got exchanged with the 14, and we got 84 in the last position. And here the remaining these n minus 1 elements, out of the 8 elements only 1 element has taken its proper position, remaining 7 elements are not at sorted in a particular order, they are still in the unordered list, that is only the largest value is correctly placed, that is 84 is correctly placed there, the remaining values are still out of order. So, here all these elements are still out of order, this is not the sorted list again. So, I need to perform the same procedure there. So, process needs to be repeated there. Now, when the process needs to be repeated mean like, so here in the 7 elements out of 8 elements the 84 has taken its proper position. So, now among the remaining 7 elements I have to bubble up the highest element. Among these elements the 61 is the highest, possibly the 61 should come in this particular position, and later the next highest is 43 has to come to the 5th position, and so on. So, some process has to be repeated there. Now, the question is how many times I supposed to repeat this particular process of the bubbling up. So, now so if there are we need to answer this now, how many times we need to repeat the bubble up procedure. The largest bubble up element takes the proper position which it must get in the sorted list. In the previous situation we can see like 84 has to take the 7th position, and it has taken the 7th position. So, after performing the bubble up procedure. So, now once we perform the bubble up procedure, then the largest element will take its proper position, and to sort the n elements we need to place n elements to their correct position which they supposed to get in the sorted order. Since 8 elements we have in the previous example, so here all the 8 elements should be arranged, should be given the positions which they supposed to take after sorting there. So, here we have taken only 8, we have given only the proper position for the element 84. So, now placing of n minus 1 elements to their correct position guarantees correct placement of all the n elements. It is not mandate that all the n elements I should arrange, so I should give the proper position in the sorted order. So, if I have n elements, then only the proper placement of n minus 1 elements is sufficient, because it will automatically give the proper position for the nth element. Say for example, if I have 2 elements, if I have 2 elements, say for example, so 25 and 12. If I need to arrange these 2 elements in the increasing order, I take the decision of giving the proper position for 25. So, then when 25 come to its right position, so then this is sufficient, I no need to give the proper position for 12. So, automatically the another element will take its proper position. Here 2 elements were there, if I give proper position for one element, the other element will automatically gets up the proper position. And similarly, if I have assume like 12, say for example, if you have 25, 12 and 17, so these are the elements. Now, so here, so the proper position for 25 is, this is the right position which is supposed to get after sorting, and the proper position for 17 is, this is the proper position which is supposed to get after sorting, and finally we have got only one position, and this position must be taken for 12 only. So, here what I can conclude is like, if I need to sort n elements, if I give the proper position for n minus 1 elements, that will guarantee that all the n elements will be in the sorted order. So, now here, so each bubbling up procedure will take the highest element to its proper position. So, here n minus 1 times I supposed to perform the bubbling up procedurally. So, bubble up n minus 1 times, because the first bubble up it has taken the 84 in its proper position, the second bubble up may take 67 to its proper position, because 67 is the next highest element, and the next bubble up may take 43 its proper position, and so on. So, this bubble up procedure or the method I should follow for n minus 1 time. So, here I have the 7 and 8 elements here, 8 minus 1 means 7 times I need to perform this particular operation there. So, that is bubble up procedure is need to perform n minus 1 times. So, next, so we will see an example of sorting the list of elements. So, here 22, 17, 43, 84, 15 and 13 here, right. So, here we have some 6 elements. So, let us see. So, bubble up procedure let us apply and sort this set of 6 elements. Now, the elements are, so here 22, so then 17, then 43 and then 84, 15 and 13. So, let me call this array as a A. The index of 22 is 0, 1, 2, 3, 4 and 5. So, as per the bubble up procedure, what I am supposed to do now is, so 22 and 17 I compare. When I compare 22 and 17, 22 is greater than the 17. So, I need to exchange these two values. After exchanging, the new list what I get is 17, 22, then this set of elements remains the same, 43, 84, 15 and 13. So, next I need to compare, so the 22 and 43. So, 22 and 43, so 22 is not greater than the 43, so no need of exchanging over there. So, I get the same set of elements here, so same list of elements. So, because I am not going to perform, so any swapping over there. So, next, so I need to compare 43 with the 84. So, when I am doing 43 with 84, even 43 is lesser than the 84. So, I need to perform any particular swapping over there. So, means I get the same list. So, here 84 and then 15 and 13. So, now, so 84 and 15 I supposed to exchange. So, because 84 is greater than the 15, I need to exchange this 84 with the 15. So, as a consequence, I get the list as 17, 22, 43 and 15 will appear here, then 84 and then 13. So, next I am supposed to go for comparing 84 and 13 now. So, 84 is greater than 13. Now, again I need to exchange that. So, 17, 22, 43, 15 and here comes 13 and here comes 84. So, now 84 has taken the proper position because no more elements existed there. So, this is after first bubble up 84 has taken its proper position. So, I call this bubble up as the term pass. So, at the end of first pass, pass 1, what the elements I am getting here is 17, 22, 43, 15, 13 and 84. 17, 22, 43, 15, 13 and 84. So, now I need to perform the same bubble up procedure for this particular list of elements now. Now, so here we have, so 1, 2, 3, 4, 5, 6 elements, out of which one element has taken its proper position. So, we are left with only the 6 elements, so 5 elements, 1, 2, 3, 4, 5 elements to get the next particular element in its proper position. So, here again we compare with the 17 and the 22 here. Now, here no need of swapping, 17 is so lesser than the 22, no need of swapping over there. So, next I do here 22 and 43 I will compare here, 22 is still lesser than the 43, no need of again swapping there. Now, here, so 43 I will compare with the 15 there. So, when I compare 43 with 15, 43 is greater than the 15, I supposed to exchange these two values. When I exchange, so I will be getting the value as, so the list of elements as 17, 22, here comes 15 and here it will be 43 and then 13 and this is already sorted. Now, 43 and 13 I supposed to compare. So, when I compare 43 and 13, so 43 is lesser than the 13, I supposed to exchange it. So, after exchange, I get 17, 22, 15 and here comes 13 and here it is 43 and now the 84 which is already sorted. Now, note that here I no need to compare this because already 84 has taken its proper position. So, here no need of comparing 43 with the 84, fine. So, at the end of pass 1, I call this as pass 1, right. So, at the end of pass 1, one element is placed properly. Now, so this is the end of pass 2, and here you can note that, so this comparison I will not be doing. So, here at the end of pass 2, the two elements are placed in at their proper position. So, you can note like, so the elements what we will be getting is 17, 22, 15, 13, 43, 84. Fine. So, 17, 22, 15, 13, 43 and 84, and you can note that 43 and 84 have taken their proper position there. Now, we need to perform the sorting of 17, 22, 15 and 13. If I take this particular list of elements, so previously you can note that here 1, 2, 3, 4, 5. So, in the first pass we have done the 5 comparisons. So, here 1, 2, 3, 4. So, here we have done the 4 comparisons. If I take the next particular list of the next pass, the same elements is supposed to get here. So, means at the end of the first pass, second pass, we have the list of elements 17, 22, 15, 13, 43 and 84. Here these two elements are already sorted. So, I compare 17 and 22, no need of swapping here. Then I have to compare 22 with 15. Here we need to swap because 22 is greater than the 15 there. So, after swapping we get 17, 15 comes here, then 22, then 13, and these elements are already sorted. So, now we have to compare 22 and 13. So, again we need to swap there because 22 is less greater than the 13. So, we get the list as 13, 22, 43 and 84. So, now we no need to compare for 22 with the 43 or to the next element 84 because so already they are in the sorted position. Obviously, they are the highest elements, so no need of swapping. Even if you compare also, the result will be like not to swap. So, here no need of doing the comparison only. This is the end of pass 3. So, in the end of pass 3, so we will be getting here these particular list of elements. You can note that end of pass 3, 3 elements have taken the proper position. So, here what we will be getting 17, 15, 13, 22, 43, 84. Fine. So, at the end of pass 1, 1 element has taken the proper position. At the end of pass 2, 2 elements have taken the proper position. At the end of pass 3, 3 elements have taken the proper position. Right. So, now we need to perform sorting on 17, 15 and 13. So, here again we do the comparison with 17 and 15. 17 is greater than 15. So, we need to exchange, and these elements remains the same. And further, now I need to compare with the 17 and 13. So, when I do the comparison, 17 is greater than the 13, I need to exchange. So, here we can note that this is the end of pass 4. At the end of pass 4, 4 elements have been successfully placed in their proper position. So, like, so at the end of pass 4 we will be having 17, 22, 43, 84 in their proper position, and only 15 and 13 may not be in the proper position. Next we have to go for the next pass. In the next pass what we will do is 15 we compare with the 13, we do the exchange because 15 is greater than the 13 there. So, now what we will get 13, 15, then 17, 22, 43, 84. So, this will give the proper position of 15. So, this is the end of pass 5 what we will be getting. Right. So, now at the end of pass 5 what we will be getting is 13, 15, 17, 22, 43 and 84. Here clearly note that out of the 6 elements we are given the proper position only for the 5 elements, and that is sufficient because the 6th element will automatically get its proper position. Here you can note that the 13 has taken its proper position. Right. So, here we have to bubble up n minus 1 time. So, the conclusion what you can come with this particular the procedure of performing the bubble sort is like, so if there are n elements, so in this context it is n is equal to 6, then the number of passes required is n minus 1, that is equal to 5 in this particular context of problem solving. So, here in general if there are n elements to be sorted, then we must take their n minus 1 passes. Each pass is bubbling up of an element. Each pass is a bubbling up of an element there. Then at the end of n minus 1th pass, that is in the 5th pass, the array get sorted over there because there are n elements. At the end of the n minus 1th pass, the array gets sorted over there. Right. So, now we need to write the algorithm so correspond to this. So, when you are writing the algorithm for this, clearly note the first statement here. So, how to start with writing the algorithm. First is supposed to read the number of elements n. So, here not necessary that you read the elements in the particular order, because unordered list we supposed to arrange them in a particular order, and we have seen like, so after reading the n number of elements, so we have to read, so here the value of n is read, number of elements, then we read the n elements of an array. So, after that, for I is equal to 1 to n minus 1. So, this is the number of passes that we are going across in the procedure of bubble sort. So, here we have seen that if there are n elements, then the number of passes will be n minus 1. That is what we have learned from the previous example solving. So, if there are n is equal to 6, the number of passes what we come across is 5, n minus 1 is 5. So, here we have to take a loop here, I is equal to 1 to n minus 1 do, because I will run from 1, 2, 3, 4 up to n minus 1 there, right. So, altogether it is n minus 1 passes. If I am starting from I is equal to 0, then it could be n passes, but we require only here n minus 1 passes. I am starting from 1 and I am taking the extreme here as n minus 1. So, here we will be having n minus 1 different passes, and in each pass what I will be doing. So, when I is equal to 1, I will be in the first pass. In the first pass, the first element will be taken its so the first highest element will take its proper position. When I is equal to 2, the 2 elements will be sorted in the proper order. When I is equal to 3, the 3 elements will be arranged in the proper order. Similarly, when I is equal to n minus 1, n minus 1 elements will be arranged in the proper order. So, that will place the nth element also in the proper order. So, now here if you see, for j is equal to 0 to n minus 1 minus I am doing here. So, this is most important here. The reason why I am doing n minus 1 minus I is, when I is equal to 1, clearly notice the first situation what we have done here. So, in case of in the first list of elements here, we have to take only up to this I value should go up to. So, here in the second loop we have taken the j value. So, j value should go up to j is equal to 0 to, so n minus I. So, when I is equal to 1, then j should go up to 0 to n minus 1 minus I. So, that is, so n minus 1 minus I means in this particular context number of elements is 1, 2, 3, 4, 5, 6. So, it should go up to 6 minus 1 is 5. So, 5 minus 1 is 4. It should go only up to, so 4, 0 to 4. So, this is the 0th element, first element, second element, third element and the fourth element, because so when I value, j value is 4 here, I will be pointing to the element 15. So, means the fourth element, this will be compared with the next element. So, here, so when I am doing the algorithmic statement here, so when j value is 0, so a of j is greater than a of j plus 1, then I will be performing the swapping over there, fine. So, for the swapping what I am trying to do here is, temp is equal to a of j is equal to a of j plus 1, a of j plus 1 is equal to temp I will be doing here. So, now, so if you want to trace this particular logic, let me reconsider the problem of the placing the 84 in its proper position. So, initially I value will be 1 and j value will be 0, let me assume. So, now here first I compare 22 and 17. So, that is, so temp I will take it as, so here a of 0 is equal to, so 22, and in the algorithm you can state like, so a of j plus 1 is taken. So, a of j plus 1 means, so it is, since j value is 0, j plus 1 means a of 1, which is equal to 17. So, a of j is greater than the a of j plus 1, then I am supposed to perform the swapping in the algorithm statement. So, what I do in swapping is, temp is equal to a of j. So, a of j means, so that is a of 0, which is equal to 22. Then what I do now is, a of 0 is equal to, that is a of j is equal to a of j plus 1. A of j plus 1 means a of 1, so which is equal to 17. So, by doing this, so here I will place the 17, right. So, now after placing the 17 there, next what I do is, a of 1 is equal to, that is a of j plus 1 is equal to the temp value. What was the temp value? A of 0 value, that was 22 there. So, a of 1 will get the value as 22. Now, the 22 has taken its proper position there. Next, j value will be incremented. When j is equal to 1 there, I will be doing the comparison of 22 and 43 there. Now, here a of j, so that is a of 1, so is not greater than a of j plus 1. A of j plus 1 means a of 2 there, right. So a of j is, j value is 1 here, 22 is not greater than the 43. I will not go for the swapping there, fine. So again the j value is incremented, so j value becomes 2. When j value becomes 2, I will be comparing with the 43 and 84. So here also the same thing, a of 2 is not greater than a of j plus 1, that is a of 3 there. So when a of 2 is not greater than a of 3, 43 is not greater than 84, I do not perform the swapping there. Again the j is incremented, so j becomes equal to 3. When j becomes equal to 3 there, so then I will be comparing with the 84 and 15. So here note that a of 3 is greater than a of 3 plus 1, that is 4. So since a of 3 is greater than a of 4, I take the temporary variable, and using this particular procedure, temp is equal to a of j is equal to a of j plus 1, a of j plus 1 is equal to temp. Using those three statements, I just do the comparison. I mean what I do now is, I will take the temporary variable, so I will take temp is equal to 84, and then here I will assign 15, and here this temporary variable I will take 84 here, right. So if I want to exchange so the contents of two jars, so what I do now is I will take additional jar, and then so if there are A, B, C are the jars, then making use of this temporary jar, I may exchange the content of the two jars. In the same way here also, if I want to exchange A of 3 and A of 4, I take the temporary variable, place the one element there, and I need to exchange, making use of the temporary variable there. So this is what happens when j is equal to 3. Next, when j is equal to 4, I need to compare these elements. So here j not necessary that it should go up to 5, because when j equals to 5, see the situation what happens. When j is equal to 5, I need to compare a of j, is it greater than a of j plus 1, right. So a of j plus 1 means it becomes like a of 6. This is not allowed, because the last index in the array is 5 only. So we should run only up to j is equal to 4. So not mandate that I should go for the j is equal to 5. If I go for j is equal to 5, so I may go wrong here, right, because I don't have the sixth element. Fine. So first element I should compare with the next element. For the next element pair, I do not have there. So here number of this was the first pass. So here, so when I was 1 there, so n minus 1 minus I means in this context it will be like 6 minus 1 minus 1, so which is equal to 4. So j has run from 0 to 4. Fine. So that's the reason. So in the algorithmic statement, so we have written like j is equal to 0 to n minus 1 minus I. What is supposed to do is, if the a of j, the current value is greater than the next value, we have to perform the sorting over there. Temp is equal to a of j equal to a of j plus 1, a of j plus 1 is equal to temp. This I should do repeatedly, right. So after doing that, so then once I comes out with this particular j loop, I will be having, so sorting the finding the highest element in its proper position, and if I do this n minus 1 times, by then I will be having the sorted list of elements. Now, so this is the program there. So to transform the algorithm into the program, this is one of the lab program. So as per the syllabus, to read the number of n elements, integer elements, and you have to perform the sorting. So applying the bubble sort procedure, you have to read here. So a of 50 you have to declare the array of 50 integer elements, n the number of elements, I, j, k, and the temp. So now these are the variables which I may require in the course of execution of this code. Now print of number of elements, I will be reading the number of elements with this particular statement, and then enter percentage d elements comma n. So I need to ask for the number of elements. If I enter 10 elements, you are supposed to enter the 10 value, 10 elements here. If I enter the number of elements as 15, then you have to give the 15 elements here. So for I is equal to 0, I less than n, I plus plus, scan of percentage d, a of I. We read all the n elements of an array. Then after that, so it is I am printing here just elements before sort. So elements before sort I am printing here, I is equal to 0, I less than n, I plus plus, print of percentage d, a of I. I am printing all the elements before the sorting, right. Next, the sorting procedure is its continuation of the bubble sort. So here the same statements of the algorithms are transformed here. So this is the number of passes n minus 1, and this is the bubbling up of the largest value there, j is equal to 0 to j less than n minus I, j plus plus. I do the comparison here, and I perform the swapping. After each pass what elements I will be getting, I can print that. And finally, if I want to print the sorted elements, I can have, after coming out of the number of passes loop, this particular loop. So, after coming out of this I loop, so I can print the elements after sorting as I is equal to 0, I less than I plus plus, all the elements gets printed over there after sorting. So, this is the way how the bubble sort algorithm can be transformed into a programming statement. Fine. So, in the next class we will see how exactly we can modify the bubble sort to improve certain redundant operation here. So, fine. So, at this moment I just end this session. So, thank you. Stop by that.